Right, today we are going to be preparing for the Unit 4 test. Hopefully you're ready and raring to go, but if there's a few things that you need to freshen up on a bit, that's what we're here for on this one. I am going to keep moving a little bit on this, so if you're watching a little bit later, feel free to pause me, fast forward me, rewind me, whatever, but when you see this initially, it's probably going to be live, so you probably won't be able to do as such. All right, starting up here. State whether the functions represent exponential growth or decay. Remember, growth is when my base value is greater than 1. And if it's between 0 and 1, that's when I see decay, except for a rare circumstance if I have a negative exponent. So here I start looking, no negative exponents, we got growth. We have growth again. Notice I keep looking at the value in the parentheses, not the other stuff. Growth, that's a lot of growth. Oops, I finally get a decay here at the end. Don't get distracted by all the other stuff. It's that base, but again, watch, if that exponent's negative, it acts as though the reciprocal of that particular base value. All right, state the y-intercept, the shift, the domain, and the range for each. Now, could I punch each of these in the calculator to get some of my information? If I want to look at a picture, I certainly can. But there are some base things that I should be able to figure out on my own. For instance, here, when I'm dealing with these, if I don't have any shifts, and I don't here, you notice no extra value up here in the exponent like there was here or at the end. It is possible to have none, and if you don't have a shift, your a value determines your intercept. Otherwise, if there had been no value here, it would have been at 0, 1. But that 2 is a multiplier. But again, that only happens when there's no shift. My domain and range, again with these, when we're working with growth and decay, my domain is always going to be infinite. Negative infinity to infinity, all reals. Because, well, they keep going forever and ever to the left and right. So I'm going to go ahead, I'm going to get the easy part of all of these done. My range, if I don't have a shift, is always going to be from 0 to infinity. Now again, if you don't remember that, you always have the option of giving yourself that little bit of a reminder. And you notice down here, okay, my lowest y value seems to be approaching 0, but then it goes on up to infinity. So that's how I know that's going to be the case. But once I start getting shifts, and again, whether it's in an exponent here, those are going to be my left and right shifts. So my shift here is going to be right 1. The only time, though, it messes with my range is if I see an up or a down shift. Because you'll notice if I do go ahead and type this one in, and if I want to have that shift in there, make sure if it's in the exponent that you put it in parentheses, because otherwise it would be like having a down 1 shift. And I graph that, notice it still approaches 0, so my range is still 0 to infinity, bottom to top. Okay, but my y-intercept's a little bit different because now I've shifted. So I can do a couple of things. I can come to here, and remember my y-intercept occurs when x equals 0, and I look, oh, there it is. Okay, so 0, 1/2, or 0.5. So again, you always can come back to the calculator, but some of the information I can get before I ever deal with that. Let me get back to here. Last one, I have 2 shifts. My left or right shift with the plus, oops, wrong place, means I'm going left 2 and down 3, because the big value on the end is always going to be my up or down shift. Here, if I want to double check for my y-intercept, again, make sure the x plus 2 is in parentheses. Otherwise, you won't end up with the right graph. And I look and I'm like, oh, looks like it's approaching down here at -3, which makes sense because we talked about the only way this is going to change is if there's an up or down shift. If this went down 3, so did my range. But that wasn't originally what I was going in here for. We were going in for the y-intercept. And again, just go to where your x value is 0, and I can get that. So again, I can take probably everything down here except possibly my y-intercept occasionally if I see those shifts. And then we can apply that back when we get down here to 8 through 10. Now, I always like paying attention to what my shifts are going to be. It kind of helps me when I'm going to graph on something like this, because I realize most of you are going to go ahead and go to the calculator on this. I don't blame you. This is mainly going to be a portion of just making sure. Again, I don't want the plus 2 in my parentheses this time because it's not up here in the exponent. So I know with it going down to, I actually like to put my asymptote in there just to remind me, okay, my graph cannot go through there or I'm going to be in trouble. And we like using the whole numbers as much as possible to be able to try and get ourselves a pretty accurate depiction here of what's going on. Oh, Harty, y'all should be yelling at me right now. I did the opposite on this. You see, if I get going too quick, it's like everybody else. I can end up making a mistake and then looking silly on like international video here. My apologies. And the good thing about this is I noticed it after I started looking at my chart, because what did I notice? My values are approaching 2. Okay, they're not approaching -2. So as I get back up here, luckily for me, I use that as a double check. Okay, so we're not using this one. We're going to be using this. So this is something we definitely want to be cautious of. Oh, let's see if we can do better on the next one here. Again, my apologies on that one, but it's better we saw it now than later. And again, this time my x and my plus 2 are both in my exponent, so I'll go ahead and get those again. I'll look at the graph for a minute. I notice there's no up or down shift, and that's true because that one's left. So my asymptote would be down at 0. And you're like, okay, so what am I supposed to do if I'm not seeing a lot as far as whole numbers, because everything here looks like a decimal? In that case, you just do the best you can with what you have to make as accurate of a picture as you can. And be content with that. And then our last one, we've got a natural log. So this is one we don't have our critical points that we can really use on something like this. So we want to make sure, take a peek here. Okay, everything's shifted over here to the right. Now remember, when we get into logarithms, our asymptotes now go from being horizontal to vertical. So that shift, where my asymptote would normally be at 0, is now going to have shifted over and become 3. But be careful. You notice how on here I don't see anything more. It doesn't mean the graph just ends there. It keeps coming down, but it runs into my asymptote, so I don't see it as well. And that's what can be helpful when I start checking these out, to remind myself, oh yeah, I've got to get all the way going down. You stop there, it's not going to be marked correct when you're doing it on your test. So again, it's always the detail stuff. I know I harp on that a lot, but it just is. When looking at this function, 100 times 5 to the negative x, Deanne thinks it must be gross since the base is greater than 1, which is sensible most of the time. Is she correct, though? No. Well, what happens? Okay. That negative exponent causes the base, my 5, to act as its reciprocal. Now, if some of you are looking for a shorter way to explain this, you could explain it as easily as the 5 to the negative x becomes 1/5 to the x, if you wanted to use more of a mathematical explanation instead of one using a sentence. Either one's fine, but again, I need to see. It can't just be negative exponent, because negative exponent can be growth or decay. It doesn't quite tell me as much. 12, if f of x equals 5 to the x and g of x is 5 to the x minus 4 plus 1, explain how to obtain g of x from f of x. What are the transformations? What are the shifts? Opposite of up there, which should be right 4. My 1 on the end is my up and down, so up 1. Evaluating, straight calculator work. So let's see here. Let's get out of here. We've got e, which again is just second natural log. Rounding the nearest hundredth. So we'd have 9/6 on that one. And then we've got 2e to 5.2. Get that on there. Now, simplifying with expressions, and several of you talked to me about these. Sometimes we can use inverses, sometimes we just use our knowledge of what a logarithm looks like in its exponential form. For instance, here, okay, I always know that e and natural log are opposites, and I know a log and its base value are inverses. This 5 and log 5 are opposites. I just end up with this. But for the rest of these, we're remembering this is my base. What power do I take it to get to the solution that I've got? And I can run that same setup on every single problem for the rest of them that I have. So I sort of have something to look at when I'm trying to figure this out. Now, we talked before about problems like 16 and 17, saying, okay, my initial idea is going to be to forget this as a fraction for a minute and say, okay, 3 to what power is 27? Well, that's 3. But this is a fraction. And 3 to the third power is 27. But this isn't 3, it's 1/3. When you go from a fraction to a whole, or a whole to a fraction, you need to be able to take the inverse, which is what we use a negative exponent for. And that's what I'm going to be doing on both of these. What do I do to 10 to get to 100? I'd square it. But again, whole number to fraction means I need the reciprocal. I need to flip it. I need to use the negative exponent. 5 to what power is 5? That would be 1, because that would work with any value. And here, if you're not sure what exponent to take to 1024, well, guess what? We're going to have to play with it a little bit. So if you're not sure, I don't know, 8. Nope, too small. 10. Yes. Play a little bit if you need to. Just kind of work that out that way. Flip over here. Rewrite the following into logarithmic or exponential form. But if it's already an exponential, then you need to put it into its log form. But I think a lot of you know this form better, so sometimes it might pay to do this one first. So I got my base, got my power, I got my answer. Not solving these, just setting them up. So then maybe I can look at this one and say, okay, now how's this work again? So now I got log. My base was there, so my base is 5. My exponent is what's on the equals side. And then the answer, 5 to the 4th is x. Good deal. So sometimes you can use the other one to help you do the opposite form. Expand the expression. Reminders. Multiply is going to become add. Divide is going to become subtract. And exponents are going to become coefficients when I'm expanding, and that's the order we want to take things in. So here I see 3 times x. That log base 2 has to go with you in each of your terms. But that's all I can do there, because I have one multiplication, split it up into addition, I'm good. Here I have a couple of things going on. if I'm looking up top, and a natural log and a log will work the same way here, those are being multiplied together. So I go ahead and do that. Is it preferred to use the parentheses? Yes, because it lets me know, ooh, that's just in the numerator. Okay. Division becomes subtract, minus the natural log of 3. I'm done. Take it in small pieces. Even if you have to do it in 2 steps, which is what I'm going to do in 24. So I've got the log of x to the negative third plus the log of y to the fourth. And that would get my numerator set for a second. I know I still have these to deal with, but we'll get there. Minus the log of 4 plus the log of y. Because again, I want to divide this whole thing. So that's why I definitely need the parentheses here. The only thing I've got left to do at this point is to swing those exponents back to the front and change them into their role as a coefficient. And if you want to distribute this out and write it as minus and minus, you could. But it's just as easy to just leave the parentheses there, so I know what I'm getting myself into. Okay, let's see here. Condense, we're just going to do the opposite of all these things. We're going to kind of work this way and work our way back. So if I see any coefficients, I'm putting them back into mode as exponents. Subtract turns back into divide. And I'm good. Coefficients back to exponents. Add becomes multiply. 5y to the 1/2. Everything just goes backwards from what I was doing up in the expand part. Ooh, lots of fun here. So let's see. So we get the log of 9 to the 1/2 plus the log of 4 to the third minus the log of 8. So I look in pieces again. Add's going to become multiply. So I've got the log. 9 to the 1/2 is the square root of 9, which is 3. 4 to the third is 64. And then minus becomes divide, 8. Now again, if you go ahead and multiply that all out, you'd end up with 192 over 8. But you also could keep going and call it the log of 24. I don't mind. As long as I see something where I know that this became multiply and divide again, whether you really simplify it or just do it here, I'm fine with either. And we're set on that. Find the inverse. Remember inverses? We're switching the x and y and we're solving for y. Here's where you've got to be careful, because I saw a couple of you doing this when we were doing this in class yesterday. I'm going to exponentiate with my base value, with the 4, which is fine. But some of you then turned this into 4x and wanted to divide something. Remember, you're solving for y. Y is by itself already. But this is 4 to the x power. If you write 4x, it's not right. There's a big difference between timesing by x and taking it to the x power. So be careful on something like that. Details, details, details. Okay. Solve equations. This goes back to what we were talking about a little bit earlier. Understanding my inverses, so e a natural log. And a log's base and its value. Here, I want to get rid of the 5. I'm going to use the log of that base as my pen runs out. Well, then we'll just use this. So when I get here, I can't just type in log like times 516 here. That's not going to work. Remember, we're doing a change of base here, which is the log of my of number, the physically bigger number here to the right, divided by the log of my base. And since it doesn't tell me what to take it to, we've been going to thousandths the most of the time. So I'll just keep doing that. If you went to the nearest hundredth or something, that's okay too. Here I'm doing just the opposite. I got the log of base 5. I'm going to exponentiate with 5. Now again, stressing, exponentiate. That is an exponent. That is 5 to the 4th power. Not 5 times 4. So I got to be careful. I'm going to get that guy set. Here, natural log. Get that out. Don't do your e to the 4th yet because we don't want to round more than once. Now that I know that my answer is e to the 4th divided by 8, e to the 4th, make sure you close that parenthesis or you'll be in for a surprise. Get my value. And then the one that seems to get everybody. Here, I can't just use log base 4 to get x alone because, well, that wouldn't work over here. So I've got to play with a change of base. I need both of these to be a base, in this case of 4. What can I do to 4 to get to 16? I can square it. And once I have those bases the same, I can actually kind of pretend that they're not there anymore. So x would equal 2 times 2x plus 3. I'm just working with the exponents at this point. So I go ahead and I distribute through, and don't forget to get all the way through there. Minus my 4x back to the other side. And divide by the negative 3. But you have to get your bases the same before you start. No options there. And then those exponents just are going to work with each other. As we work into the ones below that, again, I see the log and I want to deal with it right away, but that 2 is in the way. Fix that first. Because if I don't, I'm going to get myself into all sorts of issues here. So once I get that set, remember my log here is of base 10, so when I go to exponentiate, stressing that again, this is 10 to the 1.5 power. And again, wait till the end before you punch this in your calculator. Because that way, when I get to here, so I've got 10 to the 1.5, and I want to add 44. At this point, I can go ahead and get it in, and I haven't rounded, and then I'm going to round again. So try to wait as long as you can before you do any rounding. 34 might be the easiest one we have in this part. We have log base 5 on both sides, so we exponentiate with the 5, and that's just going to leave me with what's left over once we eliminate the log. Subtract my 2 over, divide by 2. And I'm ready to go there. But the key is always working from your goal of trying to get to x furthest away in. Here, I got to get that 1 out of there first. So I'll subtract that out. I still can't use e to get rid of ln because the negative 2 is still in the way. That needs to be divided through. So 5 halves would be 2.5, because negative divided by negative is positive. Now I'm finally ready to exponentiate. Okay? It's just like any equation. Keep getting that stuff that's furthest away out of there. So then, when we finally make it to the end, we want to know what e to the 2.5 power is. We've got it. So no stresses, no worries there. And then it gets time to start dealing with some of the story problems. And as you're doing some of these, if either when you were watching you were like, what? Or you just kind of struggled or got a wrong answer, go back, find some questions that are similar on a past quiz, on a past homework. Even go into the book and try to find out some other problems and work some more of these. Don't just sit there and kind of throw your hands up and go, well, you know, I don't know what's going on here. Here you're going to be given what the formulas are, so take advantage. Okay. Look for keywords like growing. So I start with my initial population, 1 plus 0.04, but then be careful. It'd be real easy to stick a 20 in here because you're like, well, it's 1985, now it's 2005. My time is 20. Per decade. Per 10-year period. How many 10-year periods are there from 85 to 2005? There's 2 of them. And yes, you could put this into the y equals and just scroll down to where x equals 2. But since they're only asking for the 1 bit of information, I would just type it in and get the answer. I'd literally just put in my 2, get my value. And again, we're talking about people here, so saying there's like 82 hundredths of a person, that'd be kind of, I don't even want to think about that. Okay, so let's keep working on here. So look at the context of which you're looking for an answer to a problem. People, we don't want to use partials. Vehicles, we would use cents. Okay, here, decreases, I'm going to use the same formula. So I have my initial value, but it's decreasing by 8%. What's the value after 4 years? Now, normally I'd say just type this in, but then I notice there's another question. How many years until the car is worth 10,000? Okay, I'm going to use my t this time because I can do 2 things at once if I plug it into here. So I start plugging this in. Oops, not 09. Use my x. Now, why did I do this time? Because couldn't I have just stuck a 4 there? Yes, but that's not going to help me on the second question. Here, well, there's 4. Now, some of you, if you did do it with the 4, in other words, are going to say, well, wait a minute. When I did it by itself, I got 13,253.27. Here, I'm only getting 253. Is that going to get marked wrong? No, I'm going to be able to tell which way that you did it. So either one of those are going to be acceptable. Okay? How much till the car's worth 10,000 though? That I wouldn't have wanted to guess and check. So here it looks like it's between years 7 and 8. But if you wanted to just put a year, you'd have to put 8. Because if you said 7, well, it's not quite down to 10,000 yet. Here, notice, formula is changing. You deposit your paycheck in an account that pays 3.5% annual interest compounded continuously. How long until the balance triples? Now, we've always said you can plug in whatever value you want for how much money you had, and I always do 100. Since it says triples, get to 300 at the end here. E is a value, we know that. My rate's 0.035. So here's what I'm going to do. Just the right-hand side. I'm plugging that into my calculator in the y equals. Now I want to make sure I get that x in there too. So when I go to look at the chart, now I'm trying to figure out, okay, how long is it going to take till it triples? Holy cow, it's taking a long time. So either between 31 to 32 years or just 32 years. I say find a better investment. That's a long time to have to wait. Some of you'd have to wait till you're almost 50. Yeah, that's too long to wait for 300 bucks. All right. The growth of a stock's value after its purchase in 1985 can be represented by this equation. What's the value of the stock in 85? Now remember, this is just that formula that we were using before. But we're given all the information. How much did I start with? 500 bucks, whatever was here. What's the annual rate of growth? Okay, they already added these together for me. They did 1 plus 0.04. I don't want to say 104%. That'd be great, but it's not true. I just want the growth part. And I want it as a percentage, because if you put 0.04, I'm going to assume you mean 0.04%. That's not very much. So it's always 1 plus the percentage, but it has to go back into its percentage form. And as long as you keep watching to see where it says use and what formula, these shouldn't be bad. Okay, we're going to invest $8,500, my principal. 1 plus. Make sure the 0 gets in there, even though we'd love a 45% interest rate. Compounded monthly. That's my end value. If it was weekly, it would be 52. If it was daily, it would be 365. You've got to watch for that word. And then it says n times, 10 years. This is one, and that's the only one. That's the only one with this. So again, I can use the y equals, or I can just plug it in. And I'm going to just plug it in. Plus 0.045 by 12. And we're taking that to the 12 times 10. Oops, 10. That's better. And again, it's critical that you have the 12 times 10 in parentheses, because if you don't, you're going to think you're making a whole lot more money. And again, think about it for a minute. If you put 8,500 in and it tells you you're going to get like $1 million in 10 years, that's not realistic. Wish it were that easy, but it's not. How many years will it take for an account to double its value if it collects 5% interest compounded quarterly? Okay, same formula. Excuse me. But again, they don't tell me how much. Could I use the 8,500 again? Sure, if I wanted to. I could just do that. My 5% interest quarterly. Quarter's like a fourth, just like it's a fourth of a dollar. How many years? I don't know. But I do know if I use 8,500 and I'm looking for it to double, I'm going to be looking for when my y value would be at 17,000. So this is one I need to put into the y equals part. So we got 8,500 plus 0.05 by 4. And again, make sure that 4x is in parentheses or you will be in for a surprise. Got to get back to 0 here for a minute. I know, you're like, you just went by 17,000. I just want to make sure. Yep, okay, we're in the right spot. 17,000 occurs 14 years later. And just as a matter of fact point here, I wouldn't use this to answer the question, but if you've never heard of this, if you're ever wondering how long it takes money to double, there's this thing, just sort of as an interesting fact, called the rule of 72, which basically is you take your 72, you divide by the interest, and that'll tell you how long it takes for something to double. So like if this would have said 6% interest, 72 divided by 6 is 12, and you basically could have used the 12. Even if I used 72 divided by 5, it would be like 14.4. So I'd have been pretty close. But that's just something interesting to know for future reference. We just wanted to throw that in there. All right, we got some money in our 2 bank accounts. And they actually give us the equations for both of them. How many years will it take for the 2 bank accounts to have the same balance? Okay, I have options here. I'm going to go with what I think is the easier one. And that is to go into y equals. I'm going to type both of these in at the same time. And what I'm going to do is, I could set my window so I could see where they intersect and then just look for the intersection using my calculator. That would be one option I would have. But what I'm going to do instead is I'm going to do something that I think will go a little bit quicker. And basically, what I'm going to do is I'm going to look at the chart. Let me get back to 0 here. Notice at the start that my first column is bigger. So, how long until y2 overtakes y1? How long until y2 gets bigger? Because that's the year where they're going to cross up. So I start to scroll down, and I look. I get to year 10. I'm like, nope. First column's still bigger. Nope. Oh, there it is. Okay, when I get to year 12, notice year 11, column 1's still bigger. Year 12, now this one's bigger. So, we swing this over here. About 11 to 12 years. Or again, if you want to say 12, that's fine. Okay, that's where that spot's going to come, somewhere in there. Which one's the better long-term investment? Keyword, long-term. Well, to me, once we hit year 12, every year after that, notice y is getting more and more further away in value from the first one. So I would say it's B, because after 12 years, B is always larger. And again, you could use your own way of doing it, but again, it says long term, so I can't say, well, I'm only going to leave my money in there for a year anyway, so the first one's better. Look big term, okay? But that's how we do that. Look to see where one overtakes the other. And down the home stretch we come with another word problem. Now, again, using the same type of idea that we did on the last one, we're going to do the same thing here. Okay? They give me expressions for both of these. I'm going to type them both in. So my first one is for busy bee. And the second one is for Bugsy. Now, let's see what we're being asked about this time. Get this back up. We'll be back to 0 here. Which offer is best? Now, it didn't say long-term or short-term. So I start to look at this, and it says, how many years later will Bugsy exceed the salary from Busy Bee? Okay. So Busy Bee is 1, Bugsy's 2. Okay, at the start, ooh, Busy Bee looks really good. So I start scrolling down, and just a mere 4 years later, the second column is now bigger. Okay, so that lets me answer this question, 4 years. But which job do you want? Now, if you wanted to tell me, well, I'm only using this as a stepping stone, I'm only going to be there a couple of years, so I'm using Busy Bee. Okay, but if you're there for any amount of years after 4, look at how much bigger that second column is. So to me, this is a no-brainer. Bugsy, after 4 years, I make a lot more moolah. Okay, unless you're working for a friend or something there, I mean, moolah, lots of it. Make it work. Make it rain. All right. What type of function is f of x equals 4e to the negative 3x? Linear, definitely not. That'd be something like y equals 2x. Quadratic, no, that'd be like 2x squared. So basically, I've got to figure out if this is growth or decay. So, if in doubt and you are not sure, go back to here and type it in the calculator. Now, I would hope, well, I'll keep my mouth shut until we look at the graph here. We are definitely looking at decay, but again, E typically is going to be growth, unless negative exponent makes it act the opposite of what it normally would. But again, if you look at the picture, that's okay. Okay. What's the asymptote of the graph? If you understand the shift, and normally this asymptote would have one at y equals 0, moving down to it, put it at negative 2. Could I put it into the calculator and then see what value y is approaching? Sure. But if you want to look a little bit quickness, that's an idea. All right, story problems down here at the end and we're good. So use the exponential growth function to complete the following. All right, grows exponentially. An initial population of 1,000, my P sub O. Get that in. Grows to 3,500, which would be how much I have at the end, in 4 hours. Okay, write a function for this population. In other words, find k. So I'm going to divide both sides by 1,000. I'm going to take the natural log to get rid of the e. And then to get my k value, I'm going to divide by 4. So just plug in all the values where they belong in the equation that you're given. So the natural natural log of 3.5, no, not 3.8, 3.5 divided by 4. So my k value would be like 0.313, but again, it wants a function for this. When it says write the function, basically it's saying come back to this, and all I want you to replace is the k value. Okay. There's my function. Then estimate the population at the end of 15 hours. So, what do? Well, I take what I have. I knew that I have 1,000 to start with. Ooh, not 10,000, 1,000. E to the 0.313 times my t, 15 hours. So after 15 hours, I'd have 109,399 bacteria. Holy cow. And then these last two, and I have to make an apology. The half-life here, I had a formula correct for what I was thinking before, but I messed up in that it was a half-life. I need to be using the half-life formula. So let me get that popped back in here. And we'd always talked about when they don't give us a value, we're going to start with 100, and after a half-life, we'd have half of that. That worked for 10 and 5, 2 and 1. You can make up any value you want for that. And then my time would be 5.7 years, and I need to find k. So once I have that, I'm going to divide both sides by 100. Oops, 5.7. I'm going to use my natural log. And I'm going to divide by negative 5.7. So let's see here. So my k value would be 0.122, and I'm set. So like I said, I apologize if some of you were there working this. I was putting together two problems from different places, and I got my formulas backwards there. That will not happen to you. That will not happen to you on the test. And then finally, assuming the population of a habitat is this, okay, graph the function. We'll get back to that in a minute. My initial population, so we're going to get our values down here. So y equals, and also the test itself is not quite this long, and we're doing some explanations and showing steps, so no worries. All right. So my initial value, way back as I look to see what I may have done here. Now I noticed when I went to look at the chart, I'm like, wait a minute, why is that? My initial value should always be something that's smaller than this. That seems huge. When I went back to y, notice if I don't put the parenthesis in, the second one here, that doesn't cover this because these two just cover here. I should have a number. Anybody noticing where my problem is? Oh, that's why I'm getting such a large exponentially huge number. It would help when it's a fraction if you put the divide in, right? Holy cow. That's better. So my initial population would be 1,423, because we're going to use whole numbers here. Your maximum population is always going to be at the largest t value that you have. So you're like, do I literally have to go down to 1,000? Well, I can do a couple of things. I can either go to table set and tell it to start at 1,000, which is second window. Or I could just mess with my screen, but I really don't want to do that. But here is something I'm going to do. When will the population reach 15,000? Now, you have choices here. You really do not want to sit and do this all the way through, okay? But you don't necessarily want to do a whole lot of crazy stuff here. Like my window, they're telling me this t is like my x. So it'd be from 0, to 1,000. And again, I don't want to scale that small, so 25 or 50. My y values, I've noticed, can get kind of large. So maximum is 18,000. I'll just go to 20. And when I graph it, okay, I can see how it's going here. But here's my quick way to get to 15,000. Hit trace. Notice my y value is close to it already. Now, I can't say it's 500, and I can't do this for sure. But you remember when we did table set a minute ago? I know it's somewhere between 490 and 500. If I go back to second window, and I start at 490, now I'm close. There it is. And when it comes to graphing the function, again, we're just looking for kind of a sketch here. And again, you can do that just by looking at some values, but if you know your minimum and maximums for x, and you know your initial population and your max, that's going to help you, again, back figuring out your window for this so you can get a decent sketch. And the table set lets you go anywhere you want to start within your table. Hopefully this has helped out some. If you have any issues, I'll be around in the morning too if you need to ask then, and good luck.